Today we're going to continue our last lesson on the sum and the difference identities for cosine and sine. And this time we're going to apply them to different situations and also develop the identities for tangent. So last class we saw that there are 4 different identities. Sine of x plus y, sine of x minus y, cosine x plus y, and cosine x minus y. So you would think that you could just take the cosine and distribute it into the brackets and make it cosine x minus cosine y, but the fact is that doesn't work. Instead it becomes this really complicated expression, cos x, cos y, plus sine x, sine y. And you can check that by plugging in different angles or graphing both sides of the equation, and you'll see that both sides look the same. The sine identities are similar, except for they go sine cos, cosine. Both of them have sine cos, cosine, and you put the first angle first, and then the second. First angle, second angle. The nice thing about the sine identities is that the sign in the middle of the terms is the same. There we go. So now we want to develop an identity for tangent of x plus y. Now we already know that tangent is the same as sine over cosine. So we can use the sine addition identity and the cosine addition identity to expand this out. So sine x plus y is the same as sine x cos y plus cos x sine y. And cosine identity is the same as cos cos plus sine sine. Now thankfully the question gave us the answer, so we know that it's supposed to end up looking like this. Oh boy. The good news is this expression has 4 different terms. And our expression also has 4 different terms. And I can already see that I made a mistake here with the cosine identity. The cosine identity changes the sign in the middle. There we go. Okay, so I can see on the top of this fraction that I have a plus, and this one has a plus. This denominator has minus, this one has minus. So far it's looking pretty good. I just have to figure out how can I change these terms, these 4, into these terms in red. So what would be the easiest one? Maybe how can I make the number 1? I want to get the number 1 instead of this thing here. So maybe if I take this term and divide it by itself, I can turn it into the number 1. And let's see what would happen if I did that to both of these terms. If I took this term and divided it by itself, then it would turn into the number 1, which is what I want for my first term over here. Now what if I did the same thing on the top? Well, then the cosine y's would cancel, and I would have sine x over cos x, which is tan x. Oh, look at how nice that is. Well, I can't just divide 2 of the terms by cosine x, cosine y. Whatever I do to any term on this complicated fraction, I must do to every single term. So every single term must be divided by the exact same thing. Oh look, the cosine x's will cancel here, and I'll have sine x, sine y over cos y, which is tan y. Oh, how nice. And then here I have cos x, cos y, nothing cancels, but cos x, sine x over cos x is tan x, sine x over cos y is tan y. I can see this popping out beautifully. So everything cancels here, leaving the number 1. Here I have sine x over cos x, which is tan x, and sine y over cos y, which is tan y. The denominator is perfect. On the left-hand side, the cosines cancel, leaving me with tan x. And on the right hand side, the cosines cancel, leaving me with tan y. Oops, and the plus in the middle. So there is my formula for a tangent of an addition of angles. This formula is not given to you on the formula sheet. However, if you're stuck with a situation like this that you have to prove, you can always break it up into sine and cosine. You don't actually have to memorize this tangent identity. Now for the difference identity for tangent, x minus y, we can do the same thing. This is the same as sine x minus y over cos x minus y. Then I can use my difference identities from the top. So sine is sine cos minus cosine. The sign in the middle stays the same. Whereas cosine is cos cos, sine sine, but the sign in the middle changes from negative to positive. Maybe I'll try the same trick as before. So I'll take this one on the bottom left and I'll just divide it by itself. And then I'll do that to every single term. Dividing by cos x, cos y, cos x, cos y. And now the magic happens. The cosine y's cancel, the cosine x's cancel, everything cancels down here, and nothing much cancels over here. But I get a pretty tan x minus tan y over 1 plus tan x tan y. So it's the same as the addition identity, except for I changed the plus to a minus and the minus to a plus. Now last class we saw the identity that sine of 90 minus x is the same as cosine x. So we can show that this is true just by trying a number. So is this identity true? Do we believe it? Let's try putting a number for x. So I'm going to type sine of pi over 2 minus x. Now what I'm going to do is I'm going to take the number pi over 3 and I'm going to store that number as x. So I'll take pi over 3, store that number as x, and then see what result I get. So I'll take the number pi over 3, store it as x, and now I'll do second enter, second enter. So when I put in pi over 3 instead of x, then I get, change that to a fraction, I get 1/2. So sine of pi over 2 minus pi over 3 is 1/2. Now, is that the same as cosine of pi over 3? I still have pi over 3 as my x, so let me try cosine x. It's the same. It's also 1/2. Yay! In order to prove this identity, I can use the difference identity for sine. I'm going to take this sine and expand it, making it into sine cos, cosine. The sign in the middle is the same, and then I go first angle, second angle. So the first angle is pi over 2, second angle is x. So sine pi over 2 cos x minus cos pi over 2 sine x. Now I can use my special angles. Pi over 2 is the same as 90 degrees. Gives me the point 0, 1, which is, let's see, x coordinate is cosine, and the y coordinate is sine. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this is the same as cosine x. Yay! Now, when we have differences within brackets inside of a cosine and you have to do a proof, you're always going to want to expand that difference using one of the formulas. You never want to leave a difference or a sum of two angles in your question. This becomes really long and a lot of algebra, but not so difficult. So we'll divide the paper up into left-hand side, right-hand side. So the first thing I'll do is I'll take this left-hand side and expand it. So cosine A plus cosine B squared, I can think of this kind of as x plus y all squared, which when I do that, I actually have to FOIL. It's two brackets multiplied by each other. It's not just x squared plus y squared. It's x squared plus 2xy plus y squared. So when I expand this in cosine, I get cosine squared plus 2 cos A cos B. Don't forget that part. It's easy to forget. Plus cosine B squared, cosine squared B. Same thing happens with the sine. Sine squared A, 2 sine A sine B's, and sine squared B. Ran out of space. On the right-hand side, cosine A minus B is cos cos plus sine sine. Cos cos plus sine sine. First angle, second angle, first angle, second angle. So if I expand the 2 into all the terms, I get 2 plus 2 cos A cos B plus 2 sine A sine B. Now let's see what happens on the left-hand side. We have some magic. Cosine squared plus sine squared is 1. Cosine squared B plus sine squared B is another 1. And then we have 2 cos A cos B, 2 sine A sine B left over. And 1 plus 1 is 2. Look at that. It's the same as the right-hand side. Yay! That looked really complicated at first. That turned out to be pretty nice and easy. So that sine squared plus cos squared equals 1 is such a useful formula. Now this is an important question of the sort that you're going to see on your test. Well, basically what we're going to do is work backwards. So we're going to try to look for this pattern within the difference and sum identities. So we're looking for sine cos minus cosine. So let's see where that is. So looking through the difference identities, which one is sine cos minus cos? Well, these two are minus. And these two are sine cos, so I'm thinking this one. Sine cos minus cosine. So that's the same as sine of x minus y. So going back down, since sine of x minus y is sine cos minus cosine, then I see this pattern here. What that means is that if I have pi over 8 as my first angle and 5 pi over 8 as my second angle, that means I can work backwards and just put in pi over 8 as my first angle and 5 pi over 8 as my second angle. So this will be equal to sine of pi over 8 minus 5 pi over 8. Now I've got a common denominator there, so 1 minus 5 is negative 4. And I can simplify that further to make it sine of negative pi over 2. If I look at my special angles, negative pi over 2 is the same as negative 90 degrees. And the sine value is the y-coordinate. So let's see, x is 0, y is negative 1, x gives me the cosine, y gives me the sine, so sine of negative pi over 2 is negative 1. Cool. Ooh, a hard one. How can we simplify this? Again, anytime that you see a difference of angles in brackets inside of a trig function, we're going to need to expand this using one of the identities. Here, I'm going to avoid changing this to sine and cosine, because that will make things really complicated. Instead, I'll use one of my tangent formulas. So tangent of a minus b, here it is. Tangent of x minus y is tan x minus tan y over 1 plus tan x tan y. So minus over plus. So I'm going to replace that in brackets. That's tan a minus over plus. I'll do the same thing in the denominator. Minus over plus. Gross. What a mess. So, if I change to sine and cosine here, it would get really gross and messy. That would be like fraction inside of a fraction inside of a fraction. So instead, I really want to get rid of these fractions. I don't like fractions. I've got a problem with some denominators here, but the good thing is they're both the same. So how about I do that trick where I multiply everything in the numerator and denominator by 1 plus tan a tan b. 1 plus tan a tan b. So at least when I do that on the first term, it cancels off, leaving me with just tan a minus tan b. And the second term, I get tan b plus tan a tan squared b. Now, for the second term, 1 times 1 plus tan a tan b is just 1 plus tan a tan b. And then for the second term, they cancel off with the denominator that's already there. So then I can just expand this tan b to both the terms. So tan b times tan a is tan a tan b. Tan b times tan b is negative tan squared b. Whew. Now look. The negative tan b and the positive tan b cancel. The positive tan a tan b and negative tan a tan b cancel. And I'm left with something that looks quite similar in the numerator and denominator. You can see that these two terms have a common factor. They both have a tan a, so I'm going to take that out. Tan a divided by tan a is just the number 1. And here I've got positive tan a tan b squared, so if I took out the tan a, I'd be left with just tan squared b. Uh-oh. That's not supposed to happen. I'm supposed to be able to cancel something. So let me backtrack, see where I made a mistake. Interesting. Oh, I see it. This negative sign here. This negative sign should go to everything in the second terms. So that negative will make the tan squared b on the denominator positive. There we go. So the numerator and denominator cancel, leaving me with just tan a. Now, to solve a problem like this, again, I'm going to look for this pattern, cos cos minus sine sine. And see if I can match that with one of the ones on the top, working backwards. So cos cos minus sine sine, I can see that shape right here. It's the same as cosine x plus y. So if I do cos cos minus sine sine, I get cosine x plus y, where my x is my first term and my y is my second term. Okay, and that is equal to 1/2. So let me think. Cosine of what angle is equal to 1/2? Well, I know cosine is x over r, So that means my x should be 1, r is 2. That sounds like a 1, 2, 3 triangle. 1, 2, root 3. Which, if x is 1, that means x is the short side of the triangle. So it's my 1, 2, root 3 triangle. That looks like 60 degrees. And I'll write that as pi over 3. So what that means is that inside the brackets, because I've got 10 degrees here, I shouldn't be using pi over 3, I should be using 60 degrees. So the inside of the brackets is 60 degrees. So pi plus 10 degrees is 60 degrees. So what plus 10 degrees would give me 60? That would be 50 degrees. Example 8 is really important. We want to find the value of sine A minus B. So whenever you're given a difference, always expand it using the formulas. Sine stays the same and we get A, B, A, B. Okay, now we're given some information. We're told that sine A, this whole thing, is equal to negative 3 over 5. So instead of sine A, I can write the number negative 3 over 5. It's not A that's equal to negative 3 over 5, but the whole ratio, sine A. I'm also given that cosine B is equal to negative 12 over 13. So instead of cosine B, I can write the number negative 12 over 13. So now I'm still kind of stuck because I don't know cos A or sine B. But basically, these two come from two different triangles. So maybe I can draw those out and use some of the information that was given to me in the problem. Obviously, the third quadrant thing is going to be important. So let me draw these angles in the third quadrant. I know that sine is y over r. I know that r is always positive. So that means that I've got a y value of negative 3 and an r of 5. So I can make a triangle that goes down 3 and has a hypotenuse of 5. Would I be able to find out the other side? Sure, I can use x squared plus y squared equals r squared. So x squared plus 9 is 25. So x squared is 16. So x is positive or negative 4. And because I'm in the third quadrant, I'm on the negative part of the x-axis, I must take the negative answer. So x is negative 4 because it's the third quadrant. So that means that this is my angle A right here. That means that cosine of A is x over r, so negative 4 over 5. I can also know that my cosine should be negative because of all students take calculus. Only tangent can be positive in quadrant 3. So instead of cosine A, I can now write negative 4 over 5. Okay, so that's using my yellow angle here. I need another triangle for my blue angle. This one has an x value of negative 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and a y value of 13, or sorry, r value of 13. So 13, negative 12, and we need to find out what the y coordinate is. This is my angle B. Okay, so technically B actually starts from 0, 0 and goes all the way to here. But the reference angle is just that little blue highlighted part. And technically angle A starts all the way from 0, 0 and goes all the way to here. But the reference angle for A is that yellow highlighted part. So can I find y in this case? Sure. X squared plus y squared is r squared. So 144 and y squared is 169. Y squared is 25, so y is positive or negative 5. But because y is in the third quadrant, we know that it's below the x-axis, it must be negative. So sine is y over r, which would be negative 5 over 13. So now I can put in negative 5 over 13, and just simplify that. So I have negative 3 over 5, negative 12 over 13, minus negative 4 over 5 times negative 5 over 13, giving me, and let me change it to a fraction, go into the math menu, 16 over 65. Ta-da! So to practice, try page 292, numbers 2A to F and 4 to 7. Just make sure to double check number 2E has a typo in the answer key. I'll leave you with a couple puns. This is stop, written in this form. It's a stop sign. Get it? We have sine B over tan B, which is cos B. What are these things? They're tan lines. And finally, sine divided by cosine is tangerine. Oh, math is so funny. See you next time.